This is page 70. We're looking at the characteristics of exponential functions. We already addressed the fact that when we did the pay it forward activity, the rate at which the good deeds was increasing was not linear. It was not the same number of people each day. It was growing exponentially, right? Because it was getting multiplied. Every time a new set of people had good deeds done to them, they extended the favor by paying it forward. This whole unit, Unit 5 and Unit 6, is at exponentials. Now we're going to look at the actual procedures behind it. You already explored the concept. So, first of all, this is the general formula for exponentials. Can you open your notebook to the formula sheet? I don't know if it's on there or not. It's the bright pink, page 3, 2 or 3. Let me see. It is on there. Okay, so on your formula sheet that you will have for the EOC, you don't have to highlight this. I'm highlighting it to draw your attention to it since my board's broken. I can't go up there. This is exactly what's on your formula sheet. Okay? It says exponential function, and then it has this written. Now, it doesn't explain what any of it is. You're going to have to know it. Okay? A and B are real numbers. A cannot be 0. Why can A not be 0? Look at this. What would happen if A were 0? You'd be multiplying by what? 0. Which means the whole thing would become. So this is why they have this little parameter like, hey, A can't be 0. Then it says B has to be greater than 0 or not equal to 1. Okay, I was trying to understand why it said, all right, I get it now. If B were 1, if this was a 1 right here, raised to a power, what's 1 to the second power? What's 1 to the second power? What'd you say? 1, because that's 1 squared, right? What's 1 to the third power? 1 to the sixth power. 1 to the 100th power. Which means, is anything happening? No. So this is why they're saying, hey, B can't be 1. Because nothing interesting happens if B is 1. So A can't be 0 or the whole thing disappears. B can't be 1 or you have a boring problem on your hands. Then they say B is greater than 0. Okay? Now, here's some vocab words. A is your initial value. A is your initial value. B is your growth or decay. Not both. It's one or the other. C, which there is no C over here, but as we practice, you'll start to see C pop up. C is your vertical shift. It's either going up or down. So right here, I want you to look at this example. We got 3 to the x plus 1. Okay? Look over here at your formula. B is your base. Now I know we wrote growth or decay, but it's also the word base. So we're going to draw an arrow there. We're going to say that it's also the base. It's the base of the exponent. What is B in this problem here? No. The base of the exponent is 3. What is A then? What? 1. Do you notice there's nothing in front of it? There's no additional number right here. So there's an understood 1 being multiplied here. So A is 1. And then what is your vertical shift? That would be this part on the end, very similar to when we had quadratics, that is telling it that you're going to shift it up 1. Okay? Now what I'd like you to do is to go to Delta Math, Desmos, and graph this in Desmos and put it on this paper. When you come over here to give the table, I want them in fraction form. So type it in Desmos. Three to the x plus 1, right? You can come over here and copy that and paste it. I would almost say you could, like if it were me, I would get a mouse, one of those wireless mouses for the EOC so that you can move this a lot faster. So I'm going to evaluate 3 to the negative 1 fraction. Repeat 3 to the negative 2 and give me the fraction. And now I'm going to put this on my paper. Yeah, it makes a difference, right? What is this? 4 over 3? Yes. And then, will it go back? Yes, it will. Okay, so you want to put the fraction in your table, all right, because it's a lot cleaner. But do I want to graph a fraction? So think about it like 10 over 9. When you first hear that, you probably think, I don't know how to graph that. So this is where the decimal might help, because look at the decimal. It's 1 and then some. Do you see that? This wasn't 10 over 9, was it? No, that was 4/3. 10 over 9 was this one. It's 1 and then some. 1 and then some more. You see the difference? So that's how you wrap your mind around it when you go to graph it. Now the good news is on the EOC, you won't be graphing it by hand. I don't know if they have like a widget where you just type it in or if you have to plot the points. But so we're going to put ours on here. We got 0, 2, 4, and 10. So I'm going to go left 2. What we say, 10 over 9 was 1 and then some. 4 over 3 is 1 and then some more. So I'm going to go left 2, 1 and then some. Left 1, 1 and then some more. You see what I mean? And then 0, 2, 1, 4, and 2, 10. Is that 10? Can't read. And then we can see that our curve. Now, if you drew your curve like this, it's wrong. Because look at your Desmos. Can you tell me what part of my drawing is wrong based on your Desmos? Mine is going all the way down to 0, right? What's yours doing on Desmos? And what do you notice it's hovering at? 1. Where do you think that came from in the equation? The C. So this is telling you where it's shifting up and then hovering above. So you got to draw that to represent. Oh, that was bad. Really wish my board worked. You got to draw that to represent what it's actually doing, okay? Now let's talk about some stuff around it. An exponential equation creates a curve that is either always increasing or decreasing. It's doing one or the other. It's never doing a mix of both. I'm writing. It's always increasing or decreasing. You do have this new concept of what's called an asymptote. An asymptote is an imaginary line that the graph is approaching, but it won't actually touch. So it's a line that the graph approaches, but will never touch. And this is actually not true. When you get higher up math, you learn that it actually can cross over. But for now, we'll just say. Because if there's a hole in the graph, it crosses over, but you might look at it and think it's an asymptote when it's really not. If A is plus, as in positive, then the graph will be above the asymptote. If A is negative, then the graph will be below it. The asymptote is not graphed yet. Okay, so the asymptote is that vertical shift up or down, right? So in this case, the whole graph went up 1. So I want you to take your pencil and do the best you can to make a dotted line right here. To make a dotted horizontal line running across at 1. That's your horizontal asymptote. And if you want to make a note, tell yourself, that this is your asymptote. It's a weird word. This is your asymptote. The graph will approach it, but it will not actually cross it. Now, what they're saying is if your initial value is positive, the graph will be above it. Now, I want you to go to Desmos. Right here. Yes? I want you to type a negative right in front of that 3 and watch what happens. Type a negative in front of the 3. What did it do? It flips down. Now do you notice your curve is below an imaginary asymptote? So that's what this is telling you right here. If A is positive, your curve is going to be up above it. Not necessarily growth. I'm going to erase that. It's not necessarily growth. It's just that your curve is above it. If A is negative, though, your curve is going to reflect over it and be below it. Okay? The x-intercept, that's where it crosses the what? X-axis. So in this case, what would it be? Is it crossing the x-axis? No. So in this case, for example, here, we have none. Right? So that is possible. And that's because of this shift up. What about your y-intercept? It's where it's crossing the y-axis. So in this case, what's my y-intercept? Excuse me. It's 2 right here. This is your y-intercept. Because that was your initial value. Your domain is the set of all what? X values. This particular graph, what do you notice is on the ends of it? Arrows. What do arrows mean? Keeps going. So even though my graph is stopping right here, this is what? Keeps going. And then even though this is going up, it's also going to the right. You just can't see it very well, right? If you were to take your Desmos and zoom out, zoom out, out. Keep going. I've zoomed out so far. Now this looks like an L, doesn't it? But it's definitely not an L, because watch. You see the curve? But if you zoom out so far, they can't show the curve anymore. So now it looks like an L. And you might be thinking, well, it's never going to get over here. It will. It'll just take a while. It's way up here. Like I can't even see it, right? It's shooting off the graph. So what do you think the domain is of this exponential? Negative infinity to positive infinity. And that's because it's an arrow to an arrow. Okay? You with me, Dakota? Range is the set of what? The y values. If A is positive, meaning it's like this, right here, right? Then your y values are from your asymptote up. You notice that? And if A is negative, remember it flipped down, then your y values would be down here up to your asymptote. Always sounds like I'm saying a bad word. So if you think about it, our range is dictated by that asymptote. Okay? Now, if there was no number here, then the asymptote is on the x-axis. So in this particular example, our range would be 1 to infinity. Because that's where the whole graph is. The graph is... What did I just do? The graph is above the asymptote. So it's going to hit all these y values all the way up. Keep going and going and going, right? So how do I write that? Well, can I actually see how close this gets to the asymptote? It's going to be ugly though, right? So instead of saying, oh, it's 0.9999999 or whatever, we could just say, hey, it starts at 1, but with a parentheses, because it's not going to touch the 1. And then it runs to infinity, okay? So this particular one, let's see, I'll write it right here. It's 1 to infinity for this particular graph. Now, down here is kind of a formula. So if A is positive, then it's that C value to infinity. If A is negative, it's negative infinity to the C value. So in our case, A is positive, so it's 1 to infinity. Now, what's the difference between growth and decay? Growth is when B is your base is greater than 1. Decay is when it's less than 1. But remember, it can't be 0 though. So for example, this is the graph 4 times 3 to the x. Because as I read the graph, it's going up. What's the runner doing? Going up. Here, what's the runner doing? Going down. Now, you do have to be careful though, because look at this picture right here. This picture looks like the runner would be doing what? Going down, right? This is actually when A is negative, the growth is, it's going to look like it's decreasing, okay? So you have to be careful. We're going to practice. Come on, take that. All right. growth is reflected and decay is reflected. Or you could say growth is actually decreasing. When you're trying to measure growth, it can decrease. When you're trying to measure decay, it can increase. Notice here, this was a fraction. What is that, 1/3? B was 1/3. Here, notice B was 3. So that's the difference between the two. This was what you were supposed to explore on the exploration paper that I gave you on Friday. In behavior, this is everybody's least favorite part, but it's actually not that bad. As you read the graph to the left, what's the curve doing? Is it approaching positive infinity or negative infinity? It's staying positive, right? So you're in behavior. Remember this fancy notation here? You don't have to memorize that. You just have to know how to read it, okay? This is saying as you read the graph to the left, right? As you go left, this is what this means. As you go to the left, what is the y value approaching? Okay, so here's the graph. We're going to run left. As I run left, this is why it didn't sit right with me when I was like, oh, it's never going to. As I run left, what y value is it approaching? In this particular case, this one right here. This one's approaching what? This one's approaching 0. Would you agree? Now, as you read the graph to the right, though, it's actually running straight up and approaching infinity. Now let's switch it over here. As I read the graph to the left, what's the y value approaching? Well, it's shooting up to the ceiling, so that's infinity. But as I read the graph to the right, the y value is approaching, now don't focus on the x, come back over here. What's the y value? 0. Now, I think we wrote our particular answer for this. No, we didn't. Look at this one. As I read the graph to the left, what's the y value approaching? 1. As I read the graph to the right, it's shooting to the ceiling, so it's infinity. So the one you have to worry about, right, is we call it the tail. It's the tail of the graph because it's the one that's approaching the asymptote, okay? Right. The tail of the asymptote. Anyways, so in behavior, with quadratics, do y'all remember it was always both ends up or both ends down? So it was either positive infinity, or negative. Okay, on an exponential, it's not. So you have to be careful. You have to stop and think for a second. What's the left side of the graph doing? What's the right side of the graph doing? The side that's shooting to the ceiling or shooting to the floor, that's either positive or negative infinity. But the side that's going out, like a tail, that's the one where you have to actually look at the y-axis and determine, okay?